So now we're going to consider the other half of calculus, now that we've done finite differences. So given a function and an interval, find its definite integral over that interval. So as you know, many integrals can't be done in a closed formula. Okay, and our mechanism for doing this will be to evaluate at nodes, interpolate it, and then integrate the interpolant. And the result we get is in the form I is estimated by a combination of function values at nodes So, as always, we call these points the nodes. They're the interpolation nodes, and they end up being the quadrature nodes. And then the W's are called the weights of the formula, and they do not depend on F. So they're calculated just once for that particular type of method, type of formula. And if we happen to choose equally spaced nodes, so this is our usual setup, where the spacing is the length of the interval divided by n. So the formula is called Newton-Cotes, or it's a form of Newton-Cotes quadrature formula. Okay, so the actual formula that you get depends on the kind of interpolating you do, and the most obvious interpolant of all is the piecewise linear case. So remember that we can write that interpolant as a linear combination of hat functions. Oops, this is t sub k. So the hat functions, remember, our points are equally spaced, so the hat functions are 0 almost everywhere, but they ramp up to 1 and back down to 0. So this is at node tk minus 1, this is at tk, this is at tk plus 1. All right. So that's if k is one of the tk is one of the interior points. If it's on the left boundary, right? If it's the left endpoint, then right, you just get the right side of the tent, and if it's the other endpoint, you just get the left edge of the tent. Okay. So now, integrating p, you see, the integral pulls through the sum, it pulls through this f, which is just a constant, and so all you have to do is integrate the hk's. So the integral of this one, right, it's just the area under this curve. The width here is h. The height here is 1. It's 1/2 bh. So it's 1/2 h. Okay, here, there are two triangles, right? Each one has a base of h. Each one has a height of 1. So it's 1/2, 1 times h, plus another half, 1 times h. So the integral of all these is just h. And the area under this one, the last one, is also 1/2 h. So you put it all together, and you find that I is estimated by h times 1/2 times the first function value plus the next one plus 1 times the next to last one plus 1/2 times the last one. And we're going to call this t sub f, okay, depending on f, as a function of the step size h. So this is known as the trapezoid rule, or the trapezoid formula. It is the most indispensable of all the quadrature formulas you could get. Okay, there's a beautiful error formula, so you can use Taylor series if you like, but there's a better one. It's called the Euler-Maclaurin formula. And it's really neat. So it says that the true integral is the trapezoid estimate plus some corrections. The first one is minus h squared over 12 times f prime of b minus f prime at a. And then the next one is h to the 4th over 720 f triple prime of b minus f triple prime of a, and so on. Okay, so everything only depends on derivatives of the function at the boundaries. Well, because of this term here, right, we say the method is second order accurate. So the trapezoid rule is second order accurate, which is okay, but we can do better. And the improvement is a process known as extrapolation, which is really quite a general tool, just being applied for integration here. So it's a very clever thing to know. And it's actually pretty simple-minded. So we know, we start from the fact that we know, thanks to the Euler-Maclaurin formula, we know that the true integral is the trapezoid number plus, well, I don't want to write all these details. I'm just going to write some constant times h squared. And then there's another constant times h to the 4th, and another one times h to the 6th, etc. Okay, now what's nice, or what's important, is that I don't have to know what these numbers are. I just have to know that they're there, which is nice because I don't want to have to figure out f prime and f triple prime. I may not even have them. Okay, so also then, it follows that if I replace h by 2h, 2h, right? Then I get 4, I get 4 times C2 h squared plus 16 C4 h to the 4th, and so on. And now you look at these two lines here, and you say, aha, right? I have an opportunity to get rid of that h squared term. It's simple arithmetic. If I take 4 of the second line, if I take 4 of the first line and subtract off the second line, that gets rid of the C2 terms. Then that would leave me with 4i minus I, so that leaves me with 3i, so I have to divide by 3. So in fact, I will be 1/3, 4 times the first line, minus 1 times the second line. And then the C2 terms are gone, and we get some new thing, just call it d4, h to the 4th, and then the h to the 6th comes along. All the other terms survive because their coefficients are different. But now the first error term is 4th order. So I could consider this to be a new quadrature method. Call it S sub f of h. Now, in fact, I called it S because this is also a well-known rule. It's called Simpsons Formula, or Simpsons rule. But you don't have to know that. You just derive it as an extrapolation of 2 trapezoid estimates out to 4th order accuracy. But now, why should I have to stop there? So again, if I write 2h instead of h, s sub f of 2h, plus, now I get 2 to the 4th, so I get 16 d4, h to the 4th, oops, plus 64 d6, h to the 6th, and so on. And now I look at the first line and the second line. If I take 16 of the first line and subtract off the second line, I get rid of the d4s and the h to the 4ths. So the result is I take 1/15 of 16 times the Simpson approximation at h minus the Simpson approximation for 2h, and then the next term is 6th order. In principle, I can just keep going forever. In practice, round off and instability might catch up with me. But you really can get much, much better estimates out of it by doing this. So instead of just thinking about computing the number once and then being done, right, what you do is you compute it a few times. So you try some value of delta, which is relatively large. You don't want to do a whole lot of work if you don't have to. And then maybe you try the trapezoid rule with 1/2 delta. All right, to get something better. Well, now, for free, you can combine those into S at delta. And then I could do another refinement on the trapezoid rule and get another Simpson estimate, and then combine those into some 6th order thing, whatever it is, and so on. Right? Each time I add a new entry in the first column by cutting the step size in half for trapezoid, then I can add one new row and a new column at the very end with still more accurate estimates of the integral. This process, again, the general process is called extrapolation. In the case of quadrature specifically, it's called Romberg quadrature. But it really is something we can do in a lot of different situations.